Next up we have number 11, where we have to prove that the product of two Hausdorff spaces is Hausdorff. So we start the solution by taking two Hausdorff spaces x comma tau and y comma sigma. In this space the topology is tau and here the topology is sigma. So let x comma y and u comma v be two distinct points in the product space x times y. To prove that x times y is Hausdorff, we have to now separate them using disjoint neighborhoods. Now if it happens that the first coordinates of these 2 points are different, that is x and u are different, then because they belong to the space x which is Hausdorff, they will have disjoint neighborhoods. That means there will exist open sets u and v in the topology tau such that u is the neighborhood of x, v is the neighborhood of u, and they are disjoint. But then u times y and v times y are open in the product space x times y. That is, they are open in the product topology. In fact, they are actually basis elements for the product topology such that the first point x comma y belongs to u times y, because x belongs to u and y anyway is coming from y, and the second point u comma v belongs to v times y, and these two sets are disjoint. Why are they disjoint? Because there is no common point between u and v. So you cannot possibly have an element that is common to these two sets because the first coordinate cannot belong to both u and v. That is why. So that's how you have separated these 2 points using disjoint neighborhoods in the product space. Now this is of course only one case where x is not equal to u, but we may also have x equal to u and still these 2 points can be different by having y not equal to v. But then y and v are 2 distinct points in the space y which is also Hausdorff, and so they can be separated in the space y by disjoint neighborhoods, say by w and t, which are open sets in the topology sigma on the space y, such that w is the neighborhood of y, t is the neighborhood of v, and they are disjoint. So in this case, you have these 2 sets x times w and x times t which are open in the product space. They are in fact basis elements for the product topology such that this one contains x comma y, this one contains u comma v, and they are disjoint, just like the previous case. Note that x is in x and y is in w. That's why this one is in x times w. Similarly, t contains v and u is anyway in x, so that's why you have this containment. And these 2 are disjoint because if you have a common point between them, then that common point should have a second coordinate which should belong to both w and t, which however is not possible. Okay, so that's why we have this disjoint thing. And that is why in this case also, you have been able to separate these 2 points using disjoint neighborhoods. So that tells you that in general you can do this in the space x times y, so x times y is Hausdorff. Next, number 12, where we have to show that a subspace of a Hausdorff space is Hausdorff. Let x comma tau be a Hausdorff space and y comma tau y be a subspace. So here tau y is the topology that y inherits from the topology tau. It is the subspace topology. To prove that y is Hausdorff, we take 2 distinct points y1 and y2 in y. Now we have to separate them using disjoint neighborhoods in y. Okay, so the neighborhoods have to come from the subspace topology. Now y1 and y2 being points in y are after all in x also, because y is after all a subset of x being a subspace, and x is Hausdorff. So in x we can separate these 2 points using disjoint neighborhoods. That means 2 open sets u and v will be found in the topology tau such that u is the neighborhood of y1, v is the neighborhood of y2, and they are disjoint. But then by the definition of the subspace topology tau y intersection u and y intersection v are elements in it. That means they are open in the subspace topology such that y1 belongs to y intersection u, y2 belongs to y intersection v, and they are disjoint. That means we have found disjoint neighborhoods of y1 and y2 in the subspace, and that is why the subspace is also Hausdorff. So here the solution ends.